This is example 13-67 from the end of chapter questions. It deals with the rates of chemical reactions and specifically the use of the Arrhenius equation in the two-point form. The question is framed by asking, a reaction has a rate constant of 0.011 per second at 400 degrees Kelvin and 0.689 per second at 450 Kelvin. So they give us the rate constant at two different temperatures. And we're asked to find the energy of activation, EA, for the reaction, and what is the rate constant at an intermediate temperature, 425 Kelvin. The way we're going to solve this problem is use the two-point form of the Arrhenius equation. Remember, the Arrhenius equation is ultimately used to describe the temperature dependence of our kinetics, and that manifests itself through changes in K's, the rate constant. Generally speaking, larger temperatures, larger values of K. That's what the Arrhenius equation does for us. We can use the two-point form of the Arrhenius equation, shown here, to compare rate constant values at two different temperatures, T1 and T2. These are Kelvin temperatures, not Celsius, so keep that in mind. You need to substitute in Kelvin temperatures when dealing with the Arrhenius equation. The K's are the corresponding rate constants at the two different temperatures. So let's look at using this equation to help us solve. Now, notice in the problem we're given two rate constants and two temperatures. So we probably have these variables, and we're asked to form, or to solve for, the EA, the activation energy for the reaction. Fortunately, we can do this because R is just a constant equal to 8.3145. So we have all of the known variables. My suggestion to you before you start plugging and chugging and figuring all this out is that you first start by organizing your data, because the K's and the temperatures correlate, or they go hand in hand with one another. You don't want to mix them up, otherwise bad things will happen. So I want to organize all of my information on the left-hand side before I start my calculation, so I can assure that my K's and my temperatures match up. So let's talk about the first condition. I know that under the first set of circumstances, my temperature is 400 Kelvin, and at that temperature, my rate constant was 0.0117 per second. My second condition was 450 Kelvin. And at that temperature, the observed rate constant was 0.689 per second. Both of these have the same units per second. Okay? I organized my data first to make sure I don't put the wrong number into my equation at the wrong spot. Okay? The T1 corresponds to K1, the T2 corresponds to K2, and it's important to keep all that straight. So now with my data organized, I can go to my two-point form of my Arrhenius equation and start substituting in numbers. So I need to take the ln, the natural log, of the ratio K2 over K1. Well, now that I have all my data organized, it's easy to plug in numbers where they belong. K2 is 0.689, that's the larger rate constant. K1 is the smaller rate constant, which was only 0.0117. Okay, we're given that in the problem. No big deal. Similar thing on the right side. We're going to plug in our temperatures. But again, we want to make sure we put the right temperature in the right spot. T2 is 450 Kelvin. T1 is only 400 Kelvin. 400, 450. EA is going to be our unknown variable. And as I already mentioned, our R corresponds to 8.3145. It has units of the joules attached, okay? So eventually EA is going to have joule units. So we're done with all this, all right? All right, so all we have to do now is solve, okay? So if I take this ratio, 0.689 divided by 0.0117, looks like I end up getting about 58.88. So on my calculator, I have to take the natural log of that, which works out to about 4.0756 once I hit the natural log button. Okay. Similarly, on the right side of my equation, I have to do this math. Okay. I'm going to substitute back to R so I don't have to write the 8.3145 again. But once I do the math that's in this parentheses, it turns out that that works out to 0.000277778. Okay, so that's that difference, 1 over 400 minus 1 over 450. Okay. So we're making some progress here because we're computing these values, but we're not quite done yet. So the next thing I'd like to do is to try to combine this number and this number, basically treating this as like an x variable. Okay, that's going to be kind of our unknown, this whole ratio. So I suppose if I wanted to, I could say x, a variable called x, is equal to EA over R. Okay, and then I could certainly rewrite this as 4.0756 is equal to 0.002778x, right? Because I defined x as being equal to this ratio, right? And then I can just solve for x basically by division. Okay, so it would be this divided by that. When I do that, I get 14,672.35 is my value of x, and of course that's equal to my EA, my activation energy, over R. We know that R is equal to, oops, I gotta move this a little bit, huh? Okay. Let you catch up. So I'm just doing the math, okay? I substituted in the variable x, solve for x, it's equal to 14,672, and that's equal to this ratio, activation energy over R. And again, I know my R is 8.3145. It's a constant, okay? That's given to you on the first page of your exam. You can look that up. So if that's the case, I can substitute 8.3145 in right here for R, and I can directly solve for my activation energy in this case. And if I do that, I get 121,993 joule per mole, which is approximately equal to 122 kilojoules per mole. And that's my answer for the activation energy. So EA for this reaction, 122 kilojoules per mole. All right. So that's the two-point form of the Arrhenius equation, one implementation or use of it. Now we are asked a follow-up question. So let's take a look at that and consider the follow-up question in a little bit more detail to see how we might be able to work that. What I'm going to do is erase a lot of this work, because things are going to change some. The numbers will change. But it turns out the equation that we used does not, so I'm going to leave that two-point form of my Arrhenius equation. All right. Now the second part of this problem asks us something different. We want to know now, what is the rate constant K at an intermediate temperature, 425 degrees? Well, just like before, we start by organizing our data. This new temperature is going to be 425 degrees Kelvin. So it's different than what it was before, okay? Now, before we were given the rate constant, but now we don't know what it is. We need to find it. That's going to be our variable x. ultimately. Okay? Not a big deal. We can just use the 2-point form of the Arrhenius equation to solve for a different variable. Okay? If we're going to do that, we start to substitute into the equation the things that we know. So what do we know and what don't we know? Well, we know K1 is 0.0117, but we don't know K2. That's our unknown variable. We're going to call it X. Now, notice what I did here, and I didn't talk much about this, but I used one of our data points from the original problem to substitute in. It would actually be okay if you used the other one. There's nothing wrong with that. I just chose to use this one condition at 400 degrees Kelvin. You could use 450 if you really wanted to and still arrive at the correct answer. It was just sort of a random decision that I made on the fly. All right, so don't be concerned with that. Now, I told you earlier R was just a constant. 8.3145, that remains the same. EA is our energy of activation, or activation energy for our reaction. The activation energy is always the same for a particular reaction. We know that it's 122 kilojoules per mole. Remember that R has units of joules attached, so EA must be in joule units as well. Okay, here I wrote it in kilojoule units, but I multiplied that by 1,000 to 122,000 when I put it here, because it needs to be in joules per mole to make the units jive and cancel. All right, but nonetheless, we got the ratio. Now over here, we got to plug in our temperatures. Well, what do we know about our two temperatures? Well, it looks like T1 is 400 Kelvin. T2 is 425 Kelvin. So at this point, we've plugged in all values except for one, which is our X. And of course, that's going to be our unknown value. We're going to solve for that. So if I'm working this problem algebraically, I'm going to find this, do the division on it, and then subtract the 2 on my calculator, and multiply that by this ratio. Okay? If you do that, you end up getting 2.15769. 2.15769 for this quantitative result. So basically what that means then is that the natural log of that ratio must equal 2.15769. All right, now we're still not at X, and we have to do a little bit more work. And what I would try to do at this point is to take the inverse log of both sides. All right, so basically what that would look like is we're going to take the base E and raise it to both sides. Okay, now when we do this operation, they actually negate each other, okay, which yields just X over 0.0117, okay, which is our desired ratio between our K's, our rate constant. But if I take the anti-log of one side, this side, I also need to do it to that side, which means I need to do E raised to 2.15769. And I can actually do this on my calculator. If you probably have to type in 2.15769 and then hit second function and the ln button. Usually there's a little E above the ln that's in a different color, and you know if you hit the second function, you can access that. So I think what you probably have to do is 2.15769 second function and the ln, and that should yield 8.64919 or thereabouts on your calculator. Okay, 8.64919 is what I've got right here. So we took the analog of both sides. Now, this number, 8.64919, equals my ratio between my rate constants, K1 divided by K2. It tells us basically that the K2 is 8.6419 times as big as what it was originally, okay? Now, I don't want to know what the ratio is, I want to know what the actual value of x is. What is the actual value of my K2? That's what I was asked, right? So how do I find that? Oh, I just finish off the algebra. I take the denominator and I multiply it by that to solve for x. And if I do that, I can find that x is equal to 0.101. Per second. That then is my value of K2, 0.101 per second. And I'm done with both parts of the problem, okay? So this is the use of the Arrhenius equation in two-point form. This is the equation itself. It's very useful for a couple things. I mean, one is to predict rate constants at a different temperature. That's like part B to this problem. And the other thing we did with this in part A was to determine the activation energy. That's another thing that you can do with this equation. Right? So two-point form of the Arrhenius equation. Know what these values are, what they correspond to. Know that you have to use joules here. Okay, for EA, that's very important. These have to be Kelvin temperatures. Very important. The equation itself will be given to you on an exam, so you can certainly look it up on the information sheet, which is very, very, very useful for you. I think pretty generous. So you just have to know how to use the equation, basically. The only other thing that could go wrong, I think, is the mathematics and natural log, anti-log. I'm going to see, rather than making videos on that, I may just try to see if I can find some on YouTube and just post them to the website for your use. So look for that if you're really struggling with the logarithms on your calculator and such. All right? Thanks.